Alrighty, this will be talking about 6.3, the central limit theorem. This will be the last part of chapter 6. I'm not going to go over 6.4. But in 6.3, central limit theorem, a very important theorem here in statistics, and it's going to go into our sixth objective, which is using the central limit theorem to solve problems involving sample means and large samples. So what we're going to do is we're going to select a sample of 30 adult males and find the mean measure of the triglyceride levels for the sample to be 187 milligrams per DL. You can go with either dosage limits or something. Select a second sample and find the mean to be 192 milligrams of something. Continue selecting until you have 100 samples and sample means. Let the mean of these sample means be a random variable. So the sample means become a sampling distribution of sample means. So basically, it's as someone else is doing this 30 times each, and we're all getting different means, and then we're going to bring our means together to see what we all get. So, definition of sampling distribution sample. It means is a distribution using the means computed from all possible random samples of specific size taken from a population. So let's say the population is 3,000 and we each do 30, then there'll be 100 of us that do 30. So the sample mean, and then we'll take the means of each one of those. So the sample means of samples randomly selected with replacement will be somewhat different from the population mean. The differences are caused by what we call sampling error. A sampling error is the difference between the sample measure and the corresponding population measure due to the fact that the sample is not a perfect representation of the population. There's lots of things that can play into some errors, and we'll talk about some of them. Properties of distribution of sample means. One, the mean of the sample means will be the same as the population mean. So if we take the mean of all the samples, that will be the same as the population mean. Each sample mean might be different, but all the sample means put together will be the same as the population mean. Two, the standard deviation of the sample means will be smaller than the standard deviation of the population, and it will equal the population standard deviation divided by the square root of the sample size. All right, so in example 10 here, the central limit theorem applied. This example illustrates the three properties of the central limit theorem. Suppose an 8-point quiz was given to 4 students and the results were 2, 4, 6, and 8. The population mean then would be, well, when you add 2, 4, 6 together, let's just do that real quick. So 2 plus 4 plus 6 plus 8, 2 plus 4 plus 6. There you go. 2 plus 4 plus 6 plus 8. There, okay, much better. Divided by 4 is 5. And the population standard deviation would be, I have to plug it in, calculate that. All right, give me 1 second. Two, 4, 6, 8. And then menu, stats, stat calculations, one variable stats. Okie dokie. And we are looking for the population standard deviation. So that's going to be sigma. So that comes out to 2.236. All right, so now we're going to find all possible samples of size 2 taken with replacement and find the mean of each sample. Then we're going to use the frequency distribution of the sample means, find the mean of the sample means, and the standard deviation. So what we're going to do is we have a whole bunch of different samples of just 2 people taking a quiz. And then we're going to take the mean of all these 2 people. So we got 2, 2. Mean of that would be 2, 2, 4, which is 3, 2, 6, which is 4, 2, 8, which is 5, 4, 2 would be 3, 4, 4 is 4, 4, 6 is 5, 4, 8 is 6, 6, 2 would be 4, 6, 4 would be 5, 6, 6 is 6, 6, 8 is 7, 8, 2 is 5, 8, 4 would be 6, 8, 6 would be 7, and 8, 8 would be 8. So those are the average. So basically what it is we took 2 people, they took a quiz, and this is what they got. 2 people took a quiz, that's what they got. Here's the averages. So here's all the different sample mean averages, and we're going to see just how close that is to the population mean, which was 5. Oop. So now we're going to do a frequency. How many times did we get 2? How many times we get 3, 4, all the way down? So we got 2 once, 3 2 times, 4 3 times, 5 4 times, 6 3 times, 7 2 times, and 8 1 time. So the mean of the sample means denoted by the mean of the sample means is 5. All right. So which is the mean of the population, which is what we just said at the very beginning in part 1. The mean of all the sample means will equal the population mean. Thus, again, the mean of the sample mean equals the population mean. So the standard deviation of the sample means denoted by the standard deviation of the sample means will equal the standard deviation divided by the square root of n. So earlier we got 2.236 divided by the square root of 2, because that was our sample, and that comes out to 1.581. So the standard deviation of the population divided by the sample size, again, given by this. And we can draw the histogram of the distribution sample means, and notice that the shape is approximately normal. So let me kind of sketch that real quick for a distribution. So for 2, we got 1. For 3, we got 2. For 4, we got 3. For 5, we got 4. For 6, we got 3. For 7, we got 2. And for 8, we got 1. So you can kind of see this is definitely approximately normal. All right, let's look more into this central limit theorem. So as the shape size n increases without limit, the shape of the distribution of the sample means taken with replacement from a population with a mean population and standard deviation of little sigma for population standard deviation will approach a normal distribution with a mean of the population mean and a standard deviation of the population standard deviation divided by the square root of the sample size. So for samples with sufficient size, the central limit theorem can be used to answer questions about sample means in the same manner that a normal distribution can be used to answer questions about individual values. The difference is the formula for Z is followed by the sample mean minus by population mean divided by the population standard deviation divided by the square root of the sample size. So when the original variable is normally distributed, the distribution of the sample means will be normally distributed for any sample size n. And when the distribution of the original variable is not normal, a sample size of 30 or more is needed to use a normal distribution to approximate the distribution of the sample mean. Very important there. It has to be at least 30 or more on the sample size if you don't know it is already normally distributed. So let's look at example 11 here. So example 11 says working weekends. The average time spent by construction workers who work on weekends is 7.93 hours over a period of 2 days. Assume the distribution is approximately normal and has a standard deviation of 0.8 hours. In part A, we're going to find the probability that an individual who works at that trade works fewer than 8 hours on the weekend. So to do that, we're going to draw a normal curve shave. So let me bring this up. So we're going to draw a normal curve and shade the desired area. So here's our normal curve. And then as always, the average here was a 7.93. So let's label that. And it says, find the probability that an individual who works this trade works fewer than 8 hours. So 8 would probably be about right here. So I'm looking for anything fewer than 8 hours, so a little bit past the mean. All right, now part 2, use the formula to find the z-score of the individual who works fewer than 8 hours. So in this case, this would be 8 minus 7.93 divided by the standard deviation was 0.8. And so that comes out to be about 0.0875, which we'll just see 0.09 because that's what we're going to use at our appendix E table or appendix A table E. So now using that table E, we're going to find the area at Z. So at 0.09, hopefully at this point you understand how to find that. So again, we got a 0.09 as my z-score. I need to then use that, looking at the table. So again, using the 0.09, I get 0.5359. So, and again, because I'm looking for the left, I don't have to subtract. So that does make sense. I'm a little over 0.5. So that, again, that also means that 53.59% of an employee potentially works less than 8 hours in the weekend. All right, part B then says if a sample of 40 construction workers is randomly selected, find the probability that the mean of the sample will be less than 8. So again, if we draw our thing, here we go. So here, mean again was 7.93. And we want to know what's the desired area for the mean of the sample size construction workers. Or here it is. Find the probability that the mean of the sample will be less than 8 hours. So again, it's very similar. We're looking for fewer than less hours. Fewer than 8 hours, sorry. Fewer than less. Less than 8. So in step 2 here, I'm now going to use this equation. So I got the 8 minus 7.93, standard deviation of 0.8. But now that I actually have a sample size, I'm now going to do the square root of 40. All right. And when you type that into the calculator, comes out to 0.55. So then now using the z-score of 0.55, I now get 0.7088. So again, that means that 70% of the 40 construction workers I randomly select will work less than 8 hours. All right. So that's how you can use the simple limit theorem. So find population correction factor. So the formula for the standard error of the mean is that's going to be the standard deviation divided by the square root of the sample size. Is accurate when the samples are drawn with replacement or drawn without replacement from a very large or infinite population. When sampling a finite population without replacement or a correction factor would be the square root of the population sample minus the sample size. So the population space minus the sample space divided by population minus 1. where n is population size and n is the sample size. Thus, the standard deviation of the sample means, again, we now go from the standard deviation divided by the sample size times this square root of the population size minus standard or sample size divided by population size minus 1. So the formula for z-values can now become this guy right here. So we have a gigantic formula when dealing with a finite population. So x mean minus the so sample mean minus population mean divided by population standard deviation divided by the square root of the sample size times the square root of population size minus sample size divided by population size minus 1. So I know that sounds like a lot, but really once you have all the information, you just plug it in and work it out. So if the population though is large, but the sample is small, the correction factor is U. So if the population is large, but the sample size is really small, we use this factor. In that case, the correction factor would be close to 1. All right, and then that will pretty much wrap it up. Again, I'm not going to go over the normal approximation of binomial distribution. That is not something that has to be covered in this statistics course. But if you do have questions on it, feel free to ask. It's not anything in your homework or anything. It's not going to be on the test either. But I don't mind sharing it as well. If you take another statistics course after this, you will definitely be going over that. My goal is to give you the needs that you need for this class. As always, if you ever need any more help, do reach out and I'll definitely help you. Other than that, though, I'll see you in the next video.